In this module, we're going to discuss some of the key concepts that need to be understood before designing a wave contact lens. We'll start with the importance of a good topography and continue to discuss some of the other key concepts that must be understood in order to be a successful wave designer. Okay, we'll first look at a couple topographies that would not be suitable for designing a contact lens. Now here's one extreme example. We can see that the data is over the lid. The lids are completely in the way. We have very little corneal data, and the data we do have, because of all the interference, might not be accurate. And depending on your topographer that you're using, you can open up a photo process view and see that all these rings come right over the lid here. So this is not good. Don't even think about designing a contact lens on a topography such as this. It would not come out good. And as another example of a poor topography, we have on the right side of your screen an image that some data centrally is missing, and on the left side we have full data. This is the same cornea, and what I did was just open up two designs, basically a standard design, all else being equal, just so you can see the implication of some of these small glitches in a topography. If you look here on the left where we have full data, the central curvature of this lens came out to a 724. On the right where we were missing that central data, the central curvature came out to a 753. All else is equal on these except for that one spot of data. I just want to point this out so you can see the importance that a good topography does make, and how wave lenses are built upon the topography image that you capture. Therefore, the better the topography you capture, the more successful you're going to be with wave contact lenses. The factor that you're looking for is a clear image of the cornea and lids completely out of the way. You'll notice on this image that the lids are out of the picture. They're not causing any interference. And what we're going to look at now is a couple more images of good topographies. So here I have a full set of 8 topographies, and to open them all you can just highlight the database number and drag them over to the main screen, and that will open them all individually. And once they're open, we will look at the repeatability check to make sure they are close enough. And just because their repeatability is accurate does not necessarily mean it's a good image. So you want to ensure, like we said earlier, lids are out of the way, images are clear. Some of this peripheral data here, that's okay. If it gets in the way of a lens design, we can always erase it. The main data we want is the overall general corneal topography should be accurate. And repeatability, just that little R there. And for the right eye, this one says repeatability is good. And for the left eye, it says it's very good, even though we only have 3 images of the left eye. So for this example, I'm going to close the left images, and we will use the right images. And the first thing I look at is overall shape of the topography and see if there's any outliers here. Is one not as accurate as the other? And on this one, I do notice map number 1, it doesn't have the same round shape. So all these have kind of a roundish shape up here, whereas this one sort of drops straight. So this one to me looks like an outlier, so I'm going to close that. And the next thing I will look at is just the data in general again. On map number 3 here, there's a little more peripheral distortion. Since we have better data on these two, I will delete map 3. And from here you can also look at photo process view and see if any of the rings look more clear on one versus the other. And to me this one just gets a little more distorted again in that peripheral data. So I would go with map number 4. And like I said earlier, if you don't want to use this this edge data here that is not accurate because it's off the map here, we can use the eraser tab. And to use the eraser, just click on the tab, hold your left cursor down as you swipe over the data that you don't want, and then hit OK. And as you'll see, it just swipes that out. If you make a mistake and you want to restore it, just hold your right cursor down as you swipe over and then hit OK, and that will bring some data back. But for this one, I would take it out, hit OK, and then we'll use this data. And now to extrapolate, hit the extrapolate button, and you want to click on the limbal border on the temporal side of the cornea, and then drag this white dotted line to get the data centered as best as you can. It's not necessarily on the limbus on the nasal side. You just want to center the data. So we're about here. And then click there. And then to open up a wave design, simply click on the wave logo. And the first thing that Wave is going to ask you is if you want to average the astigmatism data. So I'm going to take a moment to discuss what this means now. The reason we're prompted to average astigmatism data at this point is because the software wants to know how we want the data imported. If we average the data, it's going to blend some of the corneal curvature so that the lens won't fit as absolute. When the data is averaged, we're going to get a lens that will allow a little more tear flow behind it, have a little more motion to it, which in most cases is a good thing. We're still designing based upon the topography. We are going to align very nice with the cornea, but it won't be 100% absolute. If we select no to average astigmatism data, then we're going to get more of the absolute curvature of the cornea as our baseline for designing a contact lens. So in most cases, when we're looking for a general contact lens fit, averaging the data is a good thing. So when would we say no to average the data? When we have a lot of corneal cylinder, like limbal to limbal cylinder, when we're dealing with a fit where we want true alignment, such as orthokeratology, those are good cases when we will not average astigmatism data. But for most fits, multifocals, keratoconus, I would suggest averaging astigmatism data. So for these training videos, we're going to select yes, average astigmatism data. And you'll notice on this display, as it's opening up, we have in the upper left of our quad view, R. The R means right lens. I'm just going to hit continue here. R means right lens. 94% is how much of the data is used on the topography. And the fact that it's red means that we did average the astigmatism data. If this was blue, it would be an indicator that we did not average the astigmatism data. And you'll also note that I closed it, but as the software opened, it opened up the spectacle plane refractive error box. And if you have not already entered it in the topography, this is where you can plug in values to enter the spectral refraction, as well as an add power if you're designing a multifocal, and select which style of multifocal to use. And here I have an example of a topography where I selected to average astigmatism data, and one where I selected to not average astigmatism data. So you remember the red means data is averaged, blue means it is not averaged. All else is pretty equal. Just designed a duplicate lens with one set of data averaged, and you'll notice as we look at the cornea as it came in to the topography, when it's averaged, everything is just a little more blended. When it's not averaged, it's a little more absolute. So if we look at the actual topography here, we have this steeper cone, and as it's imported, we have more of a steep cone, and here it's not quite as steep. So it is two different data sets that we're bringing in to design our contact lens on. The next key concept to understand are that we have two tier layer modes to use as a baseline to design lenses. One is tangential tier layer mode, which is the default as you open the lens. If you right click, you'll see that we also have axial tier layer mode. This really dictates the baseline cornea that you'll be designing on. So you'll notice when I start in tangential, the lens is aligned as we open it. This is a default lens in RSIM, which we'll go over in a moment. And if I switch over to axial, you'll notice it just looks a little bit looser out in that periphery. So what I'm going to do here is open up another design where we can compare the difference between designing using axial tier layer mode and tangential tier layer mode. And what you'll find is, in general, axial just makes the lenses a little bit steeper and a little bit tighter in the periphery. I'll even put in the same power here. So these two lenses are identical. Let's see if I switch over to axial tier layer mode. Right now they are identical. I'm going to keep one in tangential, one in axial, and I will run Tools, Current Settings on both of them. And now let's compare the two. The axial lens has a central curvature of 776 and an overall sag of 1915. The tangential lens has a base curve of 783 and an overall sag of 1905. So on this cornea, on this lens, the axial design is almost a half diopter steeper and has a greater sag value of about 10 microns. The difference is axial just comes in a little steeper, tangential comes in a little flatter. In this video training series, we're going to design most of our lenses in axial mode. I have found axial mode just makes the lenses a little bit more comfortable for the patient, so I mostly design in axial tier layer mode. For our next concept to discuss with wave, I've changed topographies. We've gone with this cone here, a little decentered, and I've designed a lens that is identical in all aspects except for the design mode. So we have three design modes. We have RSIM, which is rotationally symmetric, GSIM, which is geometrically symmetric, and freeform, which is completely asymmetric. Lens 1 is an RSIM, lens 2 is a GSIM, and lens 3 is a freeform. You'll see RSIM, GSIM, and freeform. All else is equal. If I right click in the tier layer box, you can see I have 3.9 and 6.8 for the optic zone and intermediate curve. 3.968, 3.968. All lenses are 11.0. You'll see the tier layer clearance looks about even. So all else truly is equal. On an RSIM lens, it's rotationally symmetric. If we look at the back curvature, you'll see it's even in all meridians. RSIM also we cannot alter from 100% quadrant control. And our central curvature is a 746 and the base curve is a 632. The GSIM, geometrically symmetric. If we switch to back curvature view, you'll see we have two steep spots. The reason we have two when the cornea only has one is because we selected GSIM. So GSIM is always going to treat the cornea as a symmetric object when you select GSIM. If we go to the fluorescein view, you'll also note that the pattern comes out symmetric. But it's important to note that if a cornea was made symmetric on a non-symmetric cornea, in reality when you put that lens on the eye, it's not going to look like this. This lens would most likely have pooling and be too steep up in this area and bare over the cornea. The reason is when you select GSIM, you're telling the software that this cornea is a symmetric object, even though it's not. So the software is analyzing these curves to find a best fit overall because it thinks it's mostly symmetric. On most cylinder cases, you can select GSIM even though it's not 100% accurate. It still gives you a very good contact lens fit. And it's a more simple design. And we always go with a simple design because simple designs usually work better when they're well suited for the cornea. So on a cornea like this where it truly is not a symmetric cornea, do not select GSIM. And freeform, if we go to back curvature, this is the back curvature of the contact lens, you'll see it matches the cornea much better. So it has a nice steep spot over the cone, and the superior portion of the lens is not influenced by the inferior cone. So on a cornea like this, freeform is going to be your best option. You'll also note that the fluorescein pattern is not symmetric as it is in GSIM. So the key thing to understand when selecting RSIM, GSIM, or freeform is that it will be up to you to look at the cornea and decide, can I design a lens that will be rotationally symmetric and have a good fit on this cornea? Or can I design a geometrically symmetric lens and have a good fit on the cornea? Or does this cornea demand a freeform design to have its best fit? That's one of the key concepts in WAVE. If you can get that concept fully understood, most of your designs will come out successful. It really is that important to understand the difference between designing an RSIM, a GSIM, and a freeform contact lens. And the final concepts we're going to discuss in this module is this B box, which is blending, and this drop-down box, which is shape factor for asphericity in the optic zone. So minimal blending is used when this box is checked. So if I go to the back curvature view, and I'll come to this meridian where we have most change over this cone. So the back curvature view, when the line is flat, it just means the curvature is not changing. And you can always left click down, hold your cursor down, and these numbers will highlight in the upper left screen, and it'll tell you your curvature and where you are in the lens. So right now at this spot it's 7.26 millimeters or 46.5 diopters at 0.98 millimeters, and as I scroll out that begins to change. When the line goes up, the curves are getting steeper, and when it goes down, they're beginning to flatten. If I check use minimal blending, you'll see these curves become much more abrupt. So we get sharper curvature here. On most cases, you're going to want to leave that unchecked, use the minimal blending, and you'll get a smoother back curvature, which would be a more comfortable lens. Cases where you want to use minimal blending might be mainly for orthokeratology, which we'll get into in later modules. And the final box down here is shape factor, which will dictate how much asphericity is in the optic zone. When it's at 0, our optic zones, which is everything from the inside of this red control point, is a spherical or single cut curvature. If we add asphericity, then it's going to be an aspheric curve. And to better explain that, I'm going to take this lens and just open up the optic zone very wide. And you'll see how that completely changed the back curvature of the lens design. Then I'll just come to the back curvature view in any one of these meridians, and what you'll notice is this line is fairly flat. So when the line is flat on the back curvature view, the curvature is not changing. So the central curvature is a 773. If I left click, you'll see on the upper left screen we have 773 or 43.67 diopters, and then this at tells you where on the lens you are as you scroll back and forth. So this 773 stays pretty true until we get out to about here, and then it slowly adjusts just because the lens has to catch up out here. So for the most part, our lens is a spherical cut until we get to the optic zone in each meridian. If I add asphericity, you will see that now, instead of being 773 all the way out, 759, and it flattens out sooner. And the back curvature immediately matches what the cornea looks like because we've made it aspheric. If you make an aspheric lens, the placement of the optic zone really doesn't matter as much because the whole lens is aspheric anyway. So normally the placement of your optic zone is going to dictate where you change from your non-aspheric optic zone to your aspheric peripheral curves. In most cases, for align fits, I prefer to use a non-aspheric optic zone. The reason is when we have a lens that is aligned this close to the cornea, it fits very nicely, it fits very well, but we don't always get adequate tear flow behind that lens, and the lens ends up being too tight as the hours progress. So therefore, I'd prefer designing my regular aligned lens fits with a spherical optic zone, and I aim for better peripheral alignment, and to me that makes a more comfortable fit and more satisfying to my patients. But just know that this is an option available to you. For the duration of this training, we're going to not use minimal blending and not use asphericity, but it's important concepts to understand as you progress with wave. In this module, you learn some of the key concepts that are important to understand before designing a wave contact lens. To review, we went over the importance of a good topography. Remember that your topography is the foundation for your contact lens designs, so the better your topography, the better your lenses are going to be. We went over what it means to average astigmatism data or not average astigmatism data. We discussed the difference between axial tear layer mode and tangential tear layer mode. If you remember, axial just fits a little bit steeper, a little bit snugger out in the periphery, and tangential will fit a little bit more flat and a little bit looser out in the periphery. It's two different design modes you can choose between. And then we discussed RSIM, GSIM, and freeform. RSIM being rotationally symmetric, GSIM being geometrically symmetric, and freeform being completely asymmetric, and when you might want to use those on different lens designs. And then we briefly discussed the minimal blending option and what that means to the back curvature of your contact lens, and shape factor. Shape factor dictates whether or not you're going to use an aspheric back optic zone or a spherical back optic zone. If any of these concepts need to be reviewed, please watch this video again. These are very, very important concepts to understand in order to be successful with wave contact lenses. Thank you.